So yeah, great. You're here. Great. Can you hear me? I got your email, but I didn't have a chance to respond. So here, that's it. I would like to make a comment on this problem on quiz 6. Now, if you look at this comment and if you look at the solution here, you know what? I'm sorry to say this, but when you look at the solution, all of these solutions look amazingly simple. They are amazingly short and amazingly simple. And I'm sure that many of you are not happy because you did not get full credit. And on the comment section, I did write a systematic problem or a logical problem. So if I tell you that you had a systematic problem or a logical problem, that means there's a logical flaw. So your proof does not quite work. Okay, so it's hard for me to generalize because all of you have different ways to prove it, but you know what? All of them are different ways to prove, and all the methods which are incorrect, they tend to be usually longer or not efficient. But anyway, logically, it's a problem. So here, first, let me tell you. Let me explain the solution. Let me first explain the correct solution, which you should have done. Okay. So now, once again, this is the file. Quiz 6. So this is the quiz 6 answer. It's posted, and this is what it is. And as you can see, all of these things are very short. Okay, so here the first question on the quiz was this. The first question on the quiz was. The first question on the quiz was this. F of x is equal to x over x over x plus 1. So that's the function. And then this is for x is greater or equal to 0. And then what is that we have to show? We have to show that this function f is an increasing function. When you graph this, you can see that that's an increasing function. Now, when you show this, that's an increasing function. Some of you try to show me by graphs. Once again, you cannot show these things by graphs. And after this, maybe I'll go to decimals.com and I'll show you why you cannot show these by graphs. Not because they are correct and I don't accept that, it's not that. Again, the reason why I do not accept your proof by graph is because graphs are deceiving. You cannot really see what is really in there. Really on the graph, you cannot really see it. So I'm not accepting it because logically, I cannot accept that. It doesn't show. Okay? So I'm not trying to bad guy, trying to say that I'm the only one who's not accepting that, but because it doesn't work. By graphs, doesn't work. All right? So I just want to let you know that by graphs, it doesn't show. And that's why I don't accept that. So all of these things, increasing, decreasing, max, min, if you really have to show, then you have to show algebraically. You have to show it algebraically. Again, you cannot really show by graphs, but graphs will be a supporting document, and it will make things a little bit clear. It will make things clear. It will help us to understand the problem, and it will confirm our answer. But again, it cannot show. It does not show. From the logical standpoint of view, it does not show. Again, I will give you some examples after this file. Okay, all right. Should I just go there first? So I'll talk about, let me make a note of it. The graphs. Okay, so now, how do you show that this function, if this function is an increasing function? And of course, in our case, we have this restricted interval. Only the case when x is greater or equal to 0. Now, some of you, this is what you did. You found f of 0. So this is what you did. You found f of 0. What is f of 0? F of 0 is equal to what? F of 0 is equal to 0. And then you find f of 1. F of 1, you see what is f of 1? F of 1, it's going to be 1 over 2. 1 over 2. And then what is f of 2? F of 2 is equal to what? F of 2 is equal to 2 over what? 2 over 3. And then blah, blah, blah. And then you have some more. And then some of you even have this. You have the limb of f of x. And this is equal to what? Is equal to 1. This is as x approaches infinity. Okay? Now, I don't have anything, I don't have a key for infinity, so let me just write infinity here. So how about this? How about this x approaches infinity? X approaches infinity, you have this, and then that is equal to 1. Now, if you show me any of these here, does that show that what is it? It's an increasing function? Does it show that? If it satisfies all of these right here, if it satisfies all of the stuff which I just mentioned right here, if this is all true, then does that show that this function is an increasing function? So does this imply, question mark, does it imply that the function f is increasing? F is increasing? What do you think? F is increasing? Does it show that? And the answer is no, it doesn't show that. Why? The actual graph would go like this. The actual graph goes like this. Let's say we have this, and then this is 1. So this is dot 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 here. So the graph could actually be here, and then the curve can actually go like this. And who knows, maybe it goes like that, and then goes that. And then that's 1. So even though all of these are true, the actual graph could go like this. And in this case, we have max as so in this case, is that function an increasing function? No, it's not, as you can see. So all of the stuff which did not get full credit, there is a big flaw. From the logical standpoint point of view, it does not work. Now I can specifically give you an example, a very specific example where all of these are true, but the function is not increasing. So the function is not function is increasing, and the answer is this implication here is no.
Again, I'm just in my cozy corner, sitting in my beanbag chair, hanging out.
Exactly. Yeah, we know that this function is increasing, but your proof does not work. Okay, let me make this clear. We know that this f is an increased function, but your proof does not work. Get that? It's not the result. It's the proof. And so your job is to prove this. Okay, so now what I'm going to do is, let me clear all this. So now how do you prove that this is an increasing function? An increasing function means that we have this graph right here, and now let's say this is an increasing function like that. And so what is an increasing function? What is the definition of the increasing function? It means this. Pick any two values here and there. Actually, in this case, cannot be negative. So let's say we pick a value here. So let me pick this. Let me pick a value here. So if you pick any two values on the point, any 2 points on the curve, and then let's say the one on the left, let's call this guy A, and then this guy B. So this is the definition of increasing. The definition of increase so the definition of a function increasing is that we pick any 2 points on the function, on the graph of the function, and then let's say, and then we have the point on the right, and then we have the point on the left. So we have 2 points. Now the thing is that when you want to show that the function is increasing, this A and B must be arbitrary. That means that these two values are what? They are any two x values. So in other words, what? Select, the question is the randomness. Select any two values, A and B, and A is less than B. And then we pick any two x values which are not the same, and the bigger value, and then we specify which one is bigger. So in this case, the starting point is, so if you want to show that f is an increasing function, the first you have to specify two values and assign names. So in this case, what I did was I called the one, we picked two x values, A and B, and the one on the left, I call it A, and the one on the B, I call it B, so A is less than B. So this is the starting point. So now here, let me box this. Left, so if you want to show that that's an increasing function by definition, the starting point is that this must be the case. Let A is less or equal to less than B. And of course, in this case, we have a domain here. X is greater or equal to 0. That means that A must be greater or equal to 0. So I need to see this. Now these two these two X values, you don't need to call them A and B, but you can call them C or D, or you can call them X0 and X1, or X1 and X2. You can go by any names here. So this is what I need to see. If I don't see this anywhere, then the proof doesn't work. So that's the first step. And the second, I asked you to state what you have to show. What is it that we have to show? So in this case, we have to show that the point on the right, which is B in this case, the function value, this guy right here, this guy is higher. This point right here is higher than this guy right here. So we have to show this guy right here. This is show this guy. You have to show this guy right here. So basically what that means is this is f of b, this is f of b. F of b is what is greater or equal to and then f of a. Basically, this is what we have to show. Or mathematically, math people, we like to put everything on one side, and so we want to show that f of b minus f of a is greater or equal to 0. Now note that this a and b is random. A and b are any values, but a is less than b. But the bigger value, we call it b. And so now we have to show that f of b minus f of a is greater or equal to 0. So this is now the second thing I have to see. I wanted to see what you have you have to write down what you have to show. Or you can write this. If you write it this one, that's okay. Or this. Either one can be done, but if you write the one with a 0 on the right side, it's easier. Okay? So this is the first thing I need to see. If I don't see this, then there's nothing for me to grade. Next thing I wanted to see what you have to show. Sometimes, we don't say what we show, but actually it's the content. So what you have to show is somewhat of an option, writing this. This is just saying what our plan is, but that's what you have to show. Now the third part, this is the main meal. Those of you who did not get full credit, this is where the problem lies. You didn't have this part right here. And so now I'm going to make some comments about this. Okay, so what I'm going to do is let me now about this eraser, and let me erase all these parts right here. It's a mess here. So we have that first part and then the second part. And now we have to show this part right here. So let's look at this class, everybody. And especially those of you who have done really well in this class. All the A students in this class, watch out, because many of you who are getting A's in this class, there are quite a few, you still miss this part right here. So to show that f of b minus f of a is less or equal to 0, how do you show? How do you show this inequality? Well, the way we show this inequality is this. We first start with the left-hand side. And then get to 0. And in the middle, we can have equal sign, and we can have greater than sign, or we can have greater or equal to sign. We can have these kind of signs in the middle. If you look at this here, we have equal sign here, you have equal sign. We have equal sign right there, equal sign, and then we have equal sign right here, equal sign, and then we have an equal sign right here, and then at the end, we have this greater or equal to sign. So this is what we have. So at the end, we have shown that f of b minus f of a is greater or equal to 0. So now let me erase this one again. Oops. So now, how do you show? This is what we have to show. Look at this class. We start with f of b minus f of a. Start with this. Then now, let me write this, f of b minus f of a. And then this f of b is equal to this right here. And then that is this right here. And then that is that right there. Once we come to this point right here, then now it is fairly clear that this guy is greater or equal to 0. Why is that? Because b minus a is positive, because it says here a, b is bigger than a, right there. So b minus a is positive. It's actually positive. And then what? A plus 1 is positive. Why is that? Because a is greater than 0. A plus 1 is greater or equal to 1. That's positive. And the b plus 1 is greater than 1. So that's positive. So the whole thing is now bigger than 0. Is now therefore this is it. So if you have this part of this argument right here, then you would get full credit. This is the brain of this proof, basically. Now, let me make some comments. Many of you, your proof looks somewhat similar. Again, your proof looks very similar. This is what you have. You started with f of b, so here, this is what you have. This is why you only get 5 points or so. And that's this right here. So what you had was, in the proof section, this is what you had. You had f of b, and then minus f of a, and then, you know what you wrote? You wrote this. And equal to 0. You said that this is equal to what? Equal to 0. That's what you wrote. So, this is what you have to prove, but then you wrote this. Okay, so now, you know what? Once you write this, then we now have a logical problem here. So when you write this here, we know that that is something we have to show. When you repeatedly write this again, then the question is this. Did you prove this? Or did you assume this? Which one is it? Okay, now, just to make the argument clear, let me do one more step, okay? And then after this, you know what you did was this. After this is, let's say, okay, so I'm going to write this, and then you write this. And then what you have is, and then you write this. You have b over b plus 1, and then minus, and then what? A over a plus 1, a over a plus 1, and then you know what you wrote? You wrote, and then you wrote greater or equal to 0. That's what you wrote next on the next line. And then this problem here is that this is the problem right here. Writing this greater or equal to 0, this is the very problem we have. Because when you write this whole thing here, now the question is the same thing. So when you write this statement right here, did you prove this? Or did you assume this? Which one is it? Did you prove this? No, you didn't prove this. So you didn't prove this. Then did you assume this? No, you didn't prove this. You didn't. If you assume this, that's a problem. Because this is something you have to prove, not what you assume. Again, this guy right here, this statement right here you wrote, is something you must prove, not something you assume. And so if you write this and this is greater than 0, then it is a logical problem, because now, did you write this because it is true? Or did you assume this? Either way, it's going to be a problem. Did you prove this? No. If you said you proved this, then it's no, because you didn't prove this yet. Logically, it's not clear. So that's why you didn't prove this. If you say you assume this, then, well, you cannot assume this. This is something you have to prove. So either way, it's a double whammy. If you write this with a greater or equal to 0 here, it doesn't work. And then now, the next thing is write this, and then it implies you, and then you write this whole thing. And you write this whole thing, that's this big block here, and then you write this greater or equal to 0 once again. So when you write this here, then now we have a problem. Again, the problem is writing this part right here. That is exactly what the problem is. Now, so if you write this whole thing right here, and then put this in here, and then say this is greater than 0, then that's a problem. Why? Because then the question is, did you prove that? No. You didn't prove that yet. Because it's not clear. How do you know that this is bigger than 0? Or bigger or greater than 0? It's not clear. Therefore, you didn't prove this yet. But then did you assume this? No. If you assume this, then that's a problem, because you're not supposed to assume that. So you didn't prove this, or assuming this, either way it will be wrong. So here, the logic is this. You have to, in this part right here, on this part of the argument, which is the brain of the argument, you have to show that that is greater than that means you're stating that that is true. You're stating that that is true. But at this stage in time, you know what? You did not show that. So that's why it is incorrect. It's insufficient because you didn't prove this yet. Your proof is not clear. So therefore, if you said that you proved this at this time, you didn't, it's false. But then, did you assume it then? Well, you cannot assume this because if you assume that, I mean, how can you assume what you want to prove? So we have a logical problem either way. So writing this guy right here, that is exactly the problem. So, cannot have the greater equal to sign. You have to go this step by step, this is equal to this, equal to this, and then you put that is greater equal to 0 at the end. Why? Because this guy right here, you see right here, this guy, that is indeed greater or equal to 0. So now, that is a true statement. And so the conclusion is, f of b minus f of a is greater or equal to 0. It is now proven. I don't know, does that make sense? So the proof is unusually short. Of course, here the big problem was when I gave you these kind of problems here. The question is a logical problem, and you have to know the definition and know how to prove it. The actual proof, it only takes a minute. It's really short. Anybody has any question number 1? If I give you a problem like this again, do you think you can get it now? If I give you a similar problem, do you think you can get it? Do you understand?
Yes.
Yeah.
So once again, let me show you this. Here is this. If I ask you to show that a function is increasing. So once again, if I ask you to show that it is an increasing function, the starting point is this guy. I need to see this guy right here. I need to see a is less than to b. Now here the condition is that the a and the b can be any numbers. If you say that 0 is less than 1 and you only check that 0 and 1, it doesn't do. So in this case, it's any AB. The question is any AB with this condition. So here the key point is there must be any A and B. And then any A and B, and the A must be less than B. So this is what we need to see. So increasing function or decreasing function, the very starting point is I need to see this guy. Again, if I do not see this guy here, then the whole thing is wrong. Argument doesn't work. And second, I want you to state what you have to show. Okay, you have to show this guy. That's what you have to show. I'm saying what we have to show. And now the third part, this is the brain here. This is the part right here. And on this part here, you have to now show. You actually have to show it. You must show it. You must show it. You must prove it. Not just state this. If you write this statement right here, once again, write this statement right here with greater than 0, then now we have a logical problem here. Because this one here, you didn't prove it yet. You said it so. So did you prove this? Did you prove this, or are you assuming this? What are we actually doing here? Either one will be wrong in this case. You didn't prove it. You didn't prove this yet. So that's wrong. If you say you assumed it, well, you cannot assume it. You have to show it. You have to prove it. So greater than 0 here, right over here, doesn't work. Logically, that's why it's a logical problem here. Here, question is, did you prove it? Did you assume it? Either way, it's a double whammy. A double whammy. You will either get it. Either way, it's wrong. So here, I wrote this. Is that equal to this? Yeah, that's equal. They're equal here. That one we have no question. And then that is equal to that right there. That's equal. Then all the equality in this. And then when it comes to the last step, that is indeed bigger than 0. So we have now the third part. This is now the third part of the argument right here. This is the brain of the argument. This is the part where all of you got it wrong, for those of you who got 5 points or less. Anybody who has 5 points or less, this is the part which is not working. And just if you put this greater equal to 0 on every step here, then that will be a logical problem. this right here is a problem right here, because you're already making a conclusion or a hypothesis, whatever, does not work either way. All right, so now I'm going to now clear all this. So now let's go to the second problem here. The second problem is this, and now we have to show, okay, so we have this, number 2. Now this problem here, as well as the other one, is amazingly simple. So we are given a function, f of x is equal to x over x squared plus 1. And sorry that this function is very similar to the one on top. And so some of you, there are a few of you who made a mistake here. You made a copy mistake. You thought that f and the function in number 2 and the function in number 1 are the same function, but I wrote it clearly here. But few of you made that mistake of copying the same thing, okay? So now we have a given function here. Actually, that function right there, the graph actually looks like this. This graph, I think I've already shown you a couple of times, yeah. And then the maximum is actually right here. But in this case, we cannot show anything by graph. So you know what? Let me just erase this. So you have to show this algebraically, not by graph. Okay. So this is the function. So what is it that you have to show? Well, it says here to show that max f is equal to f of 1. Okay. So how do we show that statement? How do we show that this max f is equal to f of 1? How do we show that? So the max f is equal to f of 1. So now what I'm going to do is I'm going to clear this. This the statement right here, max f is equal to f of 1. That statement right here, we now translate that into a statement which we can actually show. And that statement right here, max f is equal to 1, actually means this right here. F of x minus f of 1 is less or equal to 0 for all x. So these two are same statements. These are what? They're the same statements. Same statements. But this statement, which statement? But this statement is the mathematical statement. It's the working mathematical statement. So what I'm saying is this guy right here, what I mean by this is this, okay, so let me so this statement right here, this statement meaning this statement right here. So the one which I marked in both boxes, so I have two boxes here. The first box is max f is equal to 1, and max f is equal to f of 1. That's what we have to show. And then now the other box over here is f of x minus f of 1 is less or equal to 0 for all x. This is f of x minus f of 1 is less or equal to 0. That's the same thing as saying f of x is less or equal to f of 1. And if f of x is less or equal to f of 1 for any x, for all x, of course that means that f of 1 is the biggest guy, and that shows that f of 1 is the maximum. Okay? So even though we have two statements here, the both statements, but the working mathematical statement is this guy right here. This is the working mathematical statement. This right here, it means exactly the same thing, but this is not something we can work with math. This is like an English statement. This is saying that the maximum occurs at 1, so max f is equal to f of 1. It is a true statement, but it is not the working mathematical statement. So we have to now translate this. And this is a statement which we are actually going to prove. So how do we show? How does the proof work here? The proof
Did you take off points for not writing that statement? Because in the instructions for number 2, you didn't say that you had to say what you were trying to prove. You only said that for number 1. Quiz questions.
Yeah, but this is the only way you can show, logically speaking. And in section 3.1, that's the definition of maximum. So on the problem number 2, and I did write not to, we didn't study derivatives yet. We did study derivatives, but we have not, we have not exactly studied the relationship between the derivative, and so here we are not supposed to apply derivative. So here, even if I do not say how we should prove it, this is the only way you can prove it. Does that make sense? The only way to prove that the maximum is like this is to show it to do this way. That's the only way you can prove it at this time. But we have no other methods at this point. No methods are studied at this point, and the rule on the test was you can only apply what we have covered so far. So we have not studied any theorems yet. So this is the only way. Whether I say you should prove it or not, this is the only way we know so far. Any other way does not work at this point. So here, let me show you. Okay. So here, so how does the proof start? We first start by this. We pick an x value. We pick a value, any x, and this is not any x, any value x. This is starting point. Any x. And now, what is that we have to show? We have to show that f of x minus f of 1 is less or equal to 0. That's what we have to show, must show. Then now, how do we show this? Well, the same thing. Now, we have this guy right here. And then now we have to show, not just say so. You cannot just say f of x and then what f of 1 is less or equal to 0. If you just copy this, then that will be a logical mistake again. So you cannot copy that. Cannot copy this. Here I'm just saying what I want to show. Because you have to show. How do you show? You start with f of x minus 1 and then you end up with 0 at the end. In the middle, you can have an equal sign, you can have a less than sign, or you can have less or equal to sign. In this case, we have an equal sign here, equal sign, and then we have an equal sign here, and then we have an equal sign here. And then by the time you put the last expression, this is now indeed less or equal to 0. And now, when you look at the last expression there, how do you know that this is less or equal to 0? Because the numerator has a square in there, and it has a negative. So if it's a negative, and then it's something square, that means that must be a negative number, must be less or equal to 0. And then the denominator is 2 times x squared plus 1, and so that one's 2 is positive, x squared plus 1 is positive, and so that can only be positive. It's not too hard to see, and then the conclusion is that that must be less or equal to 0. And so it is now proven. Again, this is the only way you can prove at this point. Whether I tell you what is allowed or what is not, doesn't matter, because this is the only thing we know at this point. That's the only way we can prove it. Although today, we will actually show you how to show that that's the maximum. But that procedure will be much more complicated. This is still the easier way. And as you can see, I know that some of you might get angry at me because the procedure is so short. But here, the hard part is the logical part. You have to understand what you have to show and how you show it. Again, ultimately, you can skip everything, but if you had this part right here, then you would have gotten full credit. Ultimately, it boils down to this guy right here. You know, all of these guys here, you don't have to really say anything, but you have to have this part right here, this part. This is the brain of this proof. This is the brain right here. This is the part which you have to have. Okay? If this part is not written in this form, so if you have like f of x minus f of 1 is less or equal to 0, and then you have this less or equal to 0, and then less or equal to 0 like this at every step here, then that will now be a logical problem again. Because at that point, if you say that something is less than 0, then the question is, did you prove that? Or are you assuming that? Which one is it? This is double whammy. No matter which one it is, that will be wrong. So when you write that and then less equal to 0, did you prove it? No. Did you assume it? Well, you cannot assume it. You have to prove it. But you didn't prove it. You're writing the result already. So having this less equal to 0 every step here, that will be a logical problem. You cannot make a conclusion before you prove it. And then if you look at part 2b, it's very similar, except in this case, minimum f is this. And so you have to show that that is what the greater than all x. And that's how we put it. That this is now the proof of this guy. So this is very similar. Okay, so that's the maximum. In this case, f of negative 1 is the minimum. So f of x minus f of negative 1 must be greater than 0, because we are saying that this f of negative 1 is a small value. So this must be big minus small. It has to be positive. And so that's what it is. Now that everybody understands the logic of this problem, also, of course, the definiteness was given on section 3.1, and so you had to what? You had to use that. I mean, you have to understand that is. So when you have a definition, your job is to understand what it says and know how to prove that you have to prove, and you have to know, how to use that definition. Okay, so that was the lesson here. So as you can see, the calculations are really simple, as you can see. But again, the hard part is, it doesn't mean that that's easy. The hard part is to understand what to do. That's the hard part. Okay? So now that you have seen this, I'm sure that many of you are angry at this because it was so easy, right? You're hoping that the problem would be a little bit more difficult, right? But no, the actual answer is much easier than what you wrote down on your test. Again, the actual answer, the actual correct answer is much shorter than any of your answers. It's actually shorter. It is shorter. But it has to be logically clear. That's the point. Okay? So that's the end of that. So I guess I have to just clear this. Anybody has any question on this? Again, quite a few did not prove this properly. In Calculus 1, there's not much proof there. But for those of you who will be taking more math, Calc 2, and when you go beyond Calculus 2, then actually there are a lot of proofs out there. So beyond Calculus 2, there are a lot of proofs. But Calculus 2 has more proofs than Calc 1. So in our class, we don't have that many proofs. But it is a skill for you to know, it's a skill to learn the definition. So, and then why is the definition important? Because you have to use the definition to show it. So when it says something, you have to know exactly what that means. You need to know how to write the functional definition of any term. So if you write max here, that is correct, but that's not a functional mathematical definition. That is not a working mathematical definition. So you have to convert that to this, and this is the functional mathematical definition right here. This right here is correct, but this is basically saying in English, well, max f is f of 1. That means the function, the maximum occurs at 1, but this statement is not an operating definition. This right here is the operating definition. This is the operating definition. Okay? This is the statement which we actually have to prove. So this, okay. Any questions here? Okay, so since many of you did not get it right, you know what? I'm a teacher, a math teacher, and so what I do is when I look for problems, you know what I do? I try to go back and see and then I will be looking for problems which many students missed, and then I try to give students similar types of problems again. Okay, so when a lot of people miss a certain kind of problem, then that kind of problem has a higher chance of showing up on later tests and midterms and final exam and quizzes. Okay, so you never know when these guys are showing up again. So make sure to be ready. Okay. Again, lots of problems. Math teachers, we have infinite supply problems. So no matter what problem you do, always expect to see something different. All right? You are not going to get exactly the same thing, and that will be kind of boring. Okay, so let's clear all this and all that. Okay, if you have no other questions here, here, yeah. So here, I did write the complete answer key. My plan was really not to write the answer key here, but to my surprise, more students, especially many of the A students, did not get this correct. Okay, so again, if you got 5 points or less, then that means the main part of proving has a logical problem. Okay, I think that is good enough. Also, yesterday I didn't mention, but the question number 7 on that midterm 2, I have it here. So where is that? Oh yes, Math 7 quiz, Math 7. Oh no, right here. Math 7 midterm 2, version 22, number 7 answer, and it's right here. Because I think I had a lot of pressure when I had to solve, do this in front of this. I was spending a lot of time, and so this is the entire solution right here. And if you look at part B, well, it is kind of long and messy, but it is not that long. Okay, so anyway, here everything is made much clearer. Okay, so anyway, you can follow this through, and the final answer is exactly what you see on the answer key. But this is specific case. where the V and the W were some numbers, and this is just one case. So this is the answer key to the 7. This is number 7 special case. So I wrote down problem number 7F. So this is not your problem, but if you study this problem, then your solution will be practically the same. Okay, practically the same as this solution right here. So because the general solution with a V and the W, that was much more messy, and so I didn't want to do that here, and so this is what I did instead. Yeah? So I think the last 2 days ago I got stuck here somewhere, but anyway, when I typed it in, everything was made clear, and so and then it's actually it actually goes down very pretty fast. The expression gets simplified very fast. Okay, so any questions on this one here? Does anybody have any questions on it? Does anybody have any questions from anywhere? Let's see, the yesterday's notes, let's see, is section 7, 3.32. So let me open that up. Anybody has any questions here? That's 3.2. Anybody has any questions here? Now, all the problems which I didn't do, why don't you try them on your own first? And then my recommended time for trying a problem would be about 10 minutes. So on any single problem, after spending about 10 minutes, if you're getting close to the answer, then just finish up. But after 10 minutes, you still have little idea and you don't know what's going on, then I think that is the time you want to get help. And I think the best way to get the help is what? Is at the math lab, or go to the tutor, Miss Zhang Li, our tutor, or you can always, ask me in class, or you can ask me after class. And yes, today after this class is over, yes, I will have the office hours. Okay, so those of you who have any questions, you can ask me. Today's a Friday, so I think Friday, I think is the best day for you to ask me. It's right before the weekend, so yeah. Okay, so you can ask me questions, but ask your questions somewhere. Again, I think my general time, my recommended time is this: for any problem you try, I think you should try every problem. And what you do, you try for about 10 minutes. I think 10 minutes is about a good time for you to understand. Let's say if you spend 5 minutes and you think that you have no idea what's going on, then I think you should ask somebody. Yeah? But just struggling more than 10 minutes, I think it could be a waste of time. So when you study, you don't want to waste time. And so about 10 minutes, in my opinion, I think it's a fair amount of time you should spend on any one problem. Of course, if you know how to do a problem, it doesn't even take 1 to 10 minutes. You know what? There are not many problems here which take more than 10 minutes. Okay, so anyway, in all the examples which I've not done in class, make sure that you can do it. And also, I think all of you should have access to more problems through another textbook. And I want you to scan all the problems and make sure that you can do every problem. You don't do every single problem, but make sure that you can do every problem. Okay? That's the trick. You don't do every problem, but you should be able to do every problem. You scan it. And if you think that you can do it, then you
she thinks she's a year out.
You don't do it, but you should be able to do it if the time is given to you. Okay? That's how things go. So you never skip a problem. You always read the problem and understand. So here, let me write this down here. For every problem, what do you do? What do you do?
You're waking me up, honey.
Read every problem. Read the problem
Are you breathing?
and understand.
I'm breathing.
And then your roadrunner thing.
And understand. If you think that you can do the problem, if you think that you can do the problem, then what? Then skip it. Skip the problem if you can actually do the problem. Do the problem if time is given to you. Problem if time is given. So, all right. So make sure that you skip the problem only if you think that you can actually do it. Of course, if you think that means you better know how to do it. Don't skip it when you can't do it. You don't do that here. So ideally, you should be able to do every single problem. Every single problem you must be able to do it, but you don't do every single problem. Why? Because all the problems are very, very similar. Okay? When you look at any math textbook, so there are so many problems so similar, but you make sure that you can do every one of them if the time is given. If the time is given to you, you should be able to do it. So you don't skip any problem. You read every problem and understand every problem. Okay? That's how you do it. Cannot skip any problem here. Don't just do every odd or every even. No, that kind of systematic selection is not a good thing. So you don't skip every problem. Okay? You don't skip. You read and understand every problem. Okay? All right. So let me just clear this. All right. Then if you have no questions here, I cannot do every single problem. Okay? So make sure that you can do it. So now what I'm going to do, let's now move on to section 3.3. And by the way, if you look up the list of files here, I have 1, 2, 3, and then we have 4 here. I have added 4 more files, especially the one after this. This one we'll be working on this one. I'm going to use this note, which has the first derivative. You know what? I was trying to save some time here. Again, one of the reasons why I'm wasting so much time is because my writing is kind of slow. Okay, so let's look at it. So this is section 3.3. Am I showing this page? Yes.
Yes.
Okay, so section 3.3, my goal for the day is to go over section 3.3 and section 3.5. And section 3.4 was asymptotes, and so that section we actually covered it before, okay? But it's still there, so it will type. I'll make some comments on there, but it's actually the same notes you have already seen before in chapter 1. Same exact page, I just copied it, okay? Because it is the same topic. Okay, section 3.3, this year, the section 3.3 will now come over the basis, the basic theorems, the basic practical theorems on curve sketching. Oh, and by the way, the proof of the first one is mentioned again in section 3.3, but first what was mentioned in section 3.2, and it's section 3.1. And this part right here, you know what? So you should be able to show this. So maybe I think all of you should try to prove this. This is actually section 3.1. Study is proof. Okay? You must know how to prove this, by the way. It's very basic. Okay? So how about this? I can prove it now, but why don't you try to prove this first? Now that you know what an increase or decreasing means, and so you want to prove this by definition. According to its definition. According to the definition. Definition of what? Definition of increasing. If you look at the theorem here, there's the word increasing there, and so you want to know the definition of increasing so that you can prove by the definition of increasing. So you have to show that then f is increasing. See, that's what you have to show. So you want to show that the function is increasing by the definition of increasing. All right. So again, the proof is very short. It's really a one-line proof. If you know how to prove it, it just takes about a minute. But you must know how to prove it. If you don't know how to prove it, then of course, time is not a problem. Whether you have 20 minutes or 1 hour, you will not be able to prove it. So you either prove in 1 minute or you cannot prove in 1 hour. Okay? Okay, so why don't you try it? I want you to try it. And and if you cannot prove it, then you have to ask somebody, okay? All right. And then same thing for number 2, same thing. Okay, so now let's look at the theorem here. These are the basic practical theorems on curve sketching. The theorem, first derivative test, this is called the first derivative test. That's the name of the theorem. And so now let's look at number 1. If f prime is positive, then f is increasing. Well, that makes sense.
No more audience.
If f prime of x is 0, if f prime of x is greater than 0 for all x, then f is increasing. If f prime of x is greater than 0 on an interval, then that means the function is increasing on that interval. So if it's not for all x, then it is still true on that interval. So let's say if you have, let's say, graph like, let's say like this, let's say curve like this, then in this case, from here to here, the function is increasing. And that's because the derivative is always positive. And then from here to here, the function is decreasing. And as you can see, the derivative is always negative. The tangent line will always have a negative slope. And so on. So you can apply this to any interval or the entire interval. We say that the function is increasing if the function is increasing on the entire domain. Okay? Then we say that the function is increasing. Okay, so that's that. Now let's look at the number 2. If f prime is less equal to 0, then the function is decreasing. Any question on that? Okay, so now I want you to, class, I want you to look at this very carefully. If f prime of x is greater than 0 for all x, then f is increasing. Okay, now look at that. I want you to look at this theorem right here very carefully. So let me start there. Now I'm going to now talk about the second theorem, which is called the second derivative test. Okay, the second derivative test. Now, if you look at the first part of the part 1, so second derivative test, number 1, and then look at the first part says this. If f double prime is greater than 0, then f prime is increasing. Let's look at this part right here. Is that true? If f double prime is positive, that is, if double prime is greater than 0, then f prime is increasing. So we have an arrow here. Arrow means if this, then that. If you say P implies Q, this is how we write it. P implies Q, let's say, and P and Q are what, let's say we assume that the P and the Q are some kind of statements. So these are some kind of statements. It's like this. If I get an A in the class, then I'm a good student. Well, I'm not saying that that's true, but that's a statement. If this, then this. That's what it is, right? If I'm an apple, then I'm a fruit. Okay, so P and Q are this. So this is how we write it. So if you write this right here, so if you write this, what does this mean? This means what? This means that if P, then Q. If P, then Q. That's what it means. So assuming that P and Q are statements, okay? So if I assume that the P and Q are statements, this is how you write P and the arrow Q means if P, then Q. That's what that statement means. So of course this here many times I actually put this arrow right here instead of the single arrow. So f double prime is positive. If f double prime is positive, then f prime is increasing. Is that true? Is that true? Is that true? Now, how do you know that this is true? How? Can you tell me why that is true? Okay. Class, let me write this here. If f prime is greater than 0, then what is true? Then f is what? F is an increasing function. F is f increasing. Okay, right? F is increasing. That is f is an increasing function. So now, let me now box this big theorem right here. This theorem right here, let me box this big theorem right here. Let me emphasize this. Let me mark in thick. So this right here, let me box it. This guy right here is this guy over here. I just wrote down if f of x is greater than 0, then f is increasing. So I just wrote down big over here. So everybody, do you see the statement? If f prime is greater than 0, then f is increasing. But here's the trick. When you say f here, note that we have an f here. We have an f here. So now let me write this maybe in blue. Let me write f here. And note that this f right here. They're the same guy. Now, if this theorem is this theorem of f? Is this theorem of L, or can I change the name? Instead of calling this guy f, can I call it g, or can I call it h? Replace all these f's by h. Yes or no? Well, not this f. That's part of the English word. Okay, it's not that f. But basically, the function f there, it shows up twice on this entire statement, or on this entire theorem. The letter f, that is the function f, shows up twice. So instead of f, can I replace f by g? What do you think? That f right there, can I replace f by g? Yes or no? Can I replace those two f's by g? Will that work? Yes or no?
It should.
Will it work? Okay, so can I write it this way? How about let's erase here. Then I'm going to erase this f. Then erase this f right here. And then erase this f. How come I cannot erase this f? Oh, there we go. Okay, now this. Now, do you think I can write? Let's say I can. Do you think I can write what? How about? Can I write h f g? Okay, so can I write g instead here? So do you think I can write g here and g here? Will that be the same theorem? What do you think? If I replace the function f by g, then is that the same theorem?
Yes.
Yes, it is. Okay, so I can replace that f by g, but now that means instead of f, I can put in there any function I want, right? Is that true? So now, what do you think I'm going to put in here now? Now I'm trying to show this guy here. The second derivative test, the first part of the second derivative test. What do I want to plug in? You know what? This time we know what I want to plug in is this. I want to plug in this. Here I can plug in any function here. You know what I'm going to plug in? I'm going to plug in this. Or let me use black here. How about if I plug in f prime here and f prime here? You think I can do that too? Since I can plug in any function. Can I plug in f prime instead of f there? Because f can be any function. I plug in f prime on both. What do you think? Do you think that will work too? Will that work?
Yes.
Yeah, that will work. Now if I replace this f by f prime, then now we see this. We see f prime prime. What is f prime prime?
The second derivative?
What is that?
Is that the second derivative?
Yep, that is the second derivative. You said it, right. Therefore, if f double prime is positive, then f prime is increasing. So note that this part right here, the first part of this second derivative test, this guy is actually the special case, or really the same thing as this guy here, in case you didn't know. But do they look the same? Many of you might say, oh, that's a different theorem, isn't it? No, not really. This theorem right here, this part right here, is actually the same theorem as this guy right here. They're the same guy. It looks different. So instead of f, what we have is we have f prime here. So that's why I am stressing this thing here. So when you see an F there, it does not mean that the theorem applies for function F. It doesn't mean that. F is just the name we use to show that they are the same function. So what we really have is we can undo this guy here, and undo this guy, and so we can actually take this function off. So now basically the idea is that this function right here and this function right here, we can put anything we want, just to make sure that these two guys must be the same function. That's all we need. Get that? So when you see a theorem such as this, then you should understand the theorem like this. This is how you understand. Oh, this guy here and this guy here is the same guy. That's how you should understand. So this theorem is not about the function F. It's about this guy right here. And these two, we can replace by the same name. You can put an F in there, you can put G in there. If you want to, you can put F squared there. You can put F compound F there. If you want to put F double prime, if you want to put F double prime there, you can put F prime in there. You know, you can put in anything. You can put F plus G there, then you put F plus G here. As long as the two functions are exactly the same guy, then that will be true. That's how you look at it. Is that clear? Just like x's are the same. Again, why do we use the letter x? That's because x, when you use x here and there, that means they're the same guy. So if you look at like number 3, f of x equals x to the 4th power minus 8x cubed, then what does x really mean? X really doesn't mean a thing. X in this case refers to a number, and of course, these x's, they refer to the same number. That's why you use x here and x there. But this function is not about x. X is to show what it is. So when you see x's in many different places, all we are saying is that these x's are the same guy. That's what it shows. But that is not just for numbers. It's also true for functions as well. Again, for functions. So in this case, that function right there, f, and this function right there is the same guy. As long as they're the same guy, it is true. So that's why this guy right here, it's actually the same guy as this guy right here. That's what I'm trying to point out, okay? So now, let me erase all of this here. I think I'll just save this, okay? Should I save it? I'll save it and then I'll clear all this. Okay, so now let's come back to second derivative test here. Second derivative test. If f double prime is positive, again, if f double prime is positive, then f prime is increasing. How do you know that? Oh, that is coming from here. Okay, so far so good. Now note that you have to distinguish between what is increasing and it's positive, increasing. Okay, yeah, we have increased. Okay, now let me go to the next step. If f prime is increasing, then what can you conclude about f? If f prime is increasing, what can you say about f? And the conclusion is that f is concave up. Okay, f is concave up. So I'm not going to explain to you what this f concave up really means. This term concave or concavity is actually a geometrical term. This is a graphical term. This is a geometric term. And this increasing is an algebraic term. Now, calculus is a combination of algebra and geometry, or algebra and graphs. So some terms are it's a more graphical term, and some terms are more algebraic term. Again, this increasing is an algebraic term, more than a graphical term. It's an algebraic term. But, it's also a graphical term as well, but basically it's an algebraic term. But this concavity or concave, this is a graphical term. So we have a mix of algebraic terms and the graphical terms.